Okay, so an example of a double lens system, like a microscope or a telescope or something like that. So you have your first lens, and here's your object. Okay, so your object is 8 centimeters from your first lens, and the focal length of the first lens is 6 centimeters. Your second lens is 40 centimeters from the first one. Its focal length is going to be 12 centimeters. So right now we can totally ignore the second lens and look just at the first one. So this lens is going to create, there's going to be an image created from this object and this lens, and we can find the image. So 1 over f1 is equal to 1 over do1 plus 1 over di1. So 1 over di1, 1 over f1 minus 1 over do1. So 1 over di1 will be equal to 1 over 6 minus 1 over 8. Common denominator will be 24. So 4 over 24 minus 3 over 24. So 1 over 24, di is 24 centimeters. Okay, so 24 centimeters away from this lens is our new image. So it's somewhere down here, right? This is 12, 24, I don't know, it's somewhere in here. Okay? And we can find them, and it's going to be upside down because it's real. And we can find the magnification of this. We can figure out how big it is if we wanted to, because usually the question wants to know where is the final image located and how much bigger is it than the object, the original object. Okay, so we can get our M1. It's just going to be equal to negative di over do. So negative 24 over 8. So the magnification of the first lens is negative 3. And remember, this negative just means it's inverted. Okay, but now here's the interesting thing. This distance is 24 centimeters. So what's my new DO? Because the image of the first lens becomes the object of the second lens. So this is my DO2. And if there's 40 centimeters between the two lenses, and the image, the first image is 24 centimeters away from the first guy, then he must be 16 centimeters away from the second one. And so now we can find our new DI. So again, 1 over F2 is equal to 1 over DO2 plus 1 over DI2. So 1 over DI2 is equal to 1 over F2 minus 1 over DO2. So 1 over 12 minus 1 over 16. 32/48. So 1 over di2 will be 4 over 48 minus 3 over 48, which is about 1 over 48. So 1 over di2, whoops, I didn't need to do that. I could just go to di2 since I had already written it up there. So di2 is equal to 48 centimeters. Just ignore this. Okay, so then we can find, so that means over all the way out here is my second image. And what will it be? It will actually be inverted again. But inverted again is going to mean erect this time, because it'll be upside down compared to its object, but its object was already upside down, so now it'll be right side up. Finding M2, it'll be negative di2 over do2, so negative 48 over 16. M2 will be negative 3. Now, if you did take bio, you know to get the total magnification of a microscope, you just multiply the two magnifications together. And so negative 3, the total magnification that happens in this complex or double lens system is times 9. Okay? So just to recap then, take the first lens and you just treat it as if it's solo, and you find its DI and its magnification. But then the image of that first lens becomes the object of the second one. And so a little complex math, 40 minus 24, gives us our new DO2. And so then we do the same idea, the same math again to get our second magnification. And then the total magnification will be M1 times M2. Okay, and so for practice problems, on page 389, there's two questions left there, 17 and 18. And at least one of them, 17, is a complex lens, a double lens one. And 18, I think, is concave lens. But I would like you to do another complex lens. So here it is. It's example 2. Okay, so it looks just like our example 1. The two lenses this time are 27 centimeters apart. F1 is 10 centimeters. And F2 is 9 centimeters. And DO, the object, is 30 centimeters in front of the first lens. And in case you were wondering, the height was 4 centimeters, but I don't think you need it. And so the question would be two parts. Part A would be, where is the final image located? And B would be, what is the total magnification of the system? All right. In the next video, which will be the next day, I'm going to talk about how the eye works. And then really that would be the end of this unit, except for a real cool lab. And that real cool lab, I think someday in August when we can all get together, we should all meet at the school and do the cool labs that we're missing, because we're going to miss another cool lab in the next unit, and we should just go in and play with all the cool equipment. No write-ups, just so you get to play with them. Anyway, so the cool lab is we take the lenses outside and you find their focal lengths by using the sun as the distant object and focusing the light rays on your paper, and the spot where it's focused, that's your focal length. And then you use that, and we actually do the 5 cases that we drew in an earlier video, and you can see them all. So we should play with that sometime when we can all get together. However, today, suggested problems 389, 17, 18, and this example. And I do have a practice assignment, since we're heading into a weekend when we want you to be bored. So we'll do the eye and on the next video, not for today. And in the meantime, the eye's just all theory, like how the eye works and why some of us need corrective lenses and all that jazz. And then the practice assignment. And then we'll move to atomic and quantum. Okay? Very good.